Section 7 of the Algebra of Exponents. Radical Notation. This lesson will contain two separate videos. In the first video, we'll introduce and explore the radical symbol. We'll familiarize ourselves with it by learning its properties and how they help to simplify rational exponents. In the next video, we'll learn basic operations or techniques that are used in tandem with statements involving radicals. The previous lessons focused on exponents that were rational in nature. Being rational, these exponents were essentially less than 1, unless the rational number was improper. Just as a whole number multiplied by a decimal less than 1 yields a smaller number, so too does a base with an exponent smaller than 1. Since this situation arises very frequently in all branches of mathematics, rational exponents are given a special notation, what many of us recognize as the square root symbol, or more formally, the radical symbol. Simply put, the radical symbol is shorthand for any rational exponents. There are two types of radicals. The first, any base raised to the 1/2 power, is written as the square root of that base, where the base is any real number. For example, the square root of 4 is equal to 4 to the 1/2 power, which equals 2. And the square root of 36 is equal to 36 to the 1/2 power, which equals 6. The other type of radical involves all other exponents raised to the 1/n power, where n is any real non-zero number. For example, 8 to the 1/3 power is written as the cube root of 8, which equals 2. And 32 to the -1/5 power is written as the -5th root of 32, which equals 1/2. Before the properties of radicals are covered, I need to mention the absolute value nature of radicals that they produce. Remember that when two, and by an extension, an even amount of, negative numbers are multiplied together, they produce a positive number. We also know that an even amount of positive numbers multiplied together produces a positive number as well. Now, what happens if we have a square root of a squared number, such as the square root of 2 squared, which equals the square root of 4? We know that the square root of 4 equals 2, which tells us that 2 times 2 equals 4. However, we have just established that -2 times -2 also equals 4. So what is the real correct answer of the square root of 4? The true correct answer is both -2 and +2. And we write this as plus or minus 2 to signify a positive and negative part to the answer. Therefore, we say that the nth root of b to the n equals the absolute value of b if n is even, and the nth root of b to the nth power equals b if n is odd. We get the absolute value of b only when n is even, because n signifies how many times b is multiplied together. Think about it. When we have a negative number multiplied together an even number of times, it would be positive, or negative if it's multiplied an odd number of times. Remember, a squared number or any number raised to an even power, as we now see, cannot yield a negative number. Therefore, we now remedy this by having absolute value notation, guaranteeing that we have a positive number after having a radical with an even root. We will now move on to the properties associated with radicals. The first property is the product rule for radicals. This property states that the product of two radicals is the radical of two products. For example, the square root of 4 times the square root of 9 equals the square root of 4 times 9 equals square root of 36, which equals 6. As a definition, we have the square root of a times the square root of b equals the square root of a times b. We now prove this property. As a side note, many proofs can be shown to be very simple yet concise algebraic work. Even though many high school and college algebra classes don't cover most proofs, it's very prudent to do so. So I'll work to introduce them whenever they arise, and it's ideal to do so. We first convert the radicals to their rational exponential forms. So we have the square root of a times the square root of b equals a to the 1/2 power times b to the 1/2 power. Remembering our properties of exponents, a product of two different bases with the same exponent can be multiplied together, keeping the exponents the same. Therefore, a to the 1/2 power times b to the 1/2 power equals a times b to the 1/2 power. Finally, we can convert our expression back to radical form, finishing our proof, the square root of a times b. Let's work a few examples before moving on to the next property. Number 1, the square root of 3 times the square root of 7. Remember what the product rule for radicals says. A product of radicals is a radical of products. So we simplify this by keeping the radical sign and multiplying the radicands together, which gives us the square root of 3 times 7, which equals the square root of 21. Also, note that the proof isn't an instruction manual to follow, although we could have done that to this expression. The proof is to let us see how and why certain functions and equations work. Number 2, the square root of 5 times the square root of 5. Repeating the setup from the last example, we have the square root of 5 times 5, which equals the square root of 25, which we know is 5. Notice how we had two radicals that did not have easy square roots, but when multiplied together, the root was extremely simple. Number 3, the square root of 2 times the square root of 20 times x. Now we have a variable introduced in our example. We will treat this as three different products. So therefore, we have the square root of 2 times 20 times x, which equals the square root of 40x. We're not done. While we can't take the root of 40 easily, we can definitely take part of it. Think about it this way. What factor of 40 has an easy square root? 4 does. So let's now break the product so we have a factor of 4. This gives us 4 times 10 times x under the square root. There are no rules that say we have to take the root of the whole expression. So let's take the square root of just the 4, giving us 2 times the square root of 10x. To see why that worked, simply go backwards from the proof. For example, we had 4 times 10 times x under the radical. We can work backwards from the proof and have the square root of 4 times the square root of 10 times the square root of x. Remember, just as a product of radicals is a radical of products is also a product of radicals. So we can easily solve this as 2 times the square root of 10 times the square root of x, which simplifies to 2 times the square root of 10x. Thus you can see that as long as you have a perfect root in your factor, you can just solve the square root of that one factor and leave the rest as is. Number 4, the square root of 6x squared times the square root of 25y. Our examples are getting progressively more difficult, but that's a good thing. Since the roots are the same, let's combine our products, giving us the square root of 6 times 25 times x squared times y. That's a lengthy expression, but we see two easy components, the 25 and the x squared. We can simplify this as 5 times the absolute value of x times the square root of 6y. Notice how we kept the absolute value bars on the x, since we don't know if x is positive or negative. The absolute value bars will guarantee us a positive number even if x is negative. Number 5. The square root of 4 over x times the square root of 5 over y. Here we have rational numbers under our radical signs. We can use them just the same as whole numbers, which gives us the square root of 4 times 5 over x times y. Instead of multiplying the 4 and the 5 together, notice that the 4 is a perfect root, which gives us 2 times the square root of 5 over xy. Number 6. The cube root of 5 times the cube root of 10. Our last example for this property uses cube roots. They worked exactly the same as square roots. We have the cube root of 5 times 10, which equals the cube root of 50. Since 50 doesn't have an easy factor that's a cube root, we leave this as finished. We now proceed to the quotient rule for radicals, which is proved exactly like the product rule was. First, we introduce it as the radical of a quotient is a quotient of the radicals. As a definition, we simply have the square root of a over b equals the square root of a divided by the square root of b. We prove it thus. First, we convert the radical, the square root of a over b, to exponential form, which equals a over b to the 1/2 power. We remember our rules for exponents and quotients. The exponent is applied to both the numerator and denominator. Thus, a over b to the 1/2 power equals a to the 1/2 power divided by b to the 1/2 power. We finally convert the exponents back to radical form, thus proving the property, which equals the square root of a over the square root of b. Let's do some examples with that. Number 1. The square root of 9 over 4. Let's remember our property. It says that a radical of a quotient is a quotient of radicals. So let's utilize that property now. We have the square root of 9 divided by the square root of 4, which simplifies to 3 over 2. Number 2. The square root of 64 divided by the square root of 65. Here we have a perfect square on the numerator, but not the denominator. Let's use our rule first. We get the square root of 64 divided by the square root of 65. We know the square root of 64, but not 65. So the final answer is 8 divided by the square root of 65. Number 3. The fifth root of negative 32 divided by 243. This radical might seem intimidating because of the high index. Not many roots come to mind of the fifth root, not to mention we have a negative number. First, let's use our property. We have the fifth root of negative 32 divided by the fifth root of 243. Recall that a fifth root means what number multiplied 5 times equals the radicand. Since we have 32 on the numerator, the root must be small. The number 243 will be a bit bigger. Here's a trick. 32 is an even number, so dividing it 5 times will continuously yield negative numbers. And if we keep it up, we get down to 2 on the fifth level. This means the fifth root of 32 is 2. And because the index of the radical is an odd number, the numerator is negative 2. For the denominator, 243 isn't an even number, so we can't divide it evenly 5 times to see what the fifth root is. So we work on the other way around. Let's start with 3 and climb up 5 times. We have 3, next is 9, next is 27, next is 81, and 81 times 3 just so happens to be 243. So our answer is actually quite simple. Negative 2 divided by 3. Number 4. The square root of x squared divided by 9. Here we have a variable in the radical of a quotient. Starting with the quotient rule, we have the square root of x squared divided by the square root of 9. Now we have a square root of a square, and we don't know what the value of x would be, so we have to utilize the absolute value for the radicals. We end up with the absolute value of x divided by 3. In the next lesson, we'll discuss operational work on the radicals we developed in this lesson. We'll add and subtract them, multiply them, and show a unique operation called rationalization, and some work on the indices of radicals.